Okay, sir.
All right. Ashi.
The meeting is live, sir. Why, sir?
The title of the movie is The Black Sheep. It will out to YouTube by 7 p.m.
Everybody's getting F.
Thanks, sir.
This result is not 0, 0. Everybody got 0. They didn't write anything. I didn't.
Good afternoon, folks. You must have been taught the first part of this course. Now we're going to look at relative motion today and other topics. Let's look at frame of reference. A frame of reference is a set of coordinates with a clock attached so that we can measure distances and velocities. You can see X, Y, and Z, and then that's the clock attached. Of course, to get velocity, you must find displacement and find the time taken. Now, every motion is referred to a frame of reference, which is why the name is frame of reference. When you say a body is moving at 40 meters per second, you are in effect referring to a fixed frame of reference. Say a fixed spot on the surface of the earth. And the body is in relation, it's moving relative to that point on the surface of the earth. You can also imagine there's also a frame of reference attached to the body itself. With respect to this frame, the body is at rest. Now let us think about this. You are in a train moving at 10 meters per second relative to an observer by the side of the rail track. So somebody beside you on the train, you are at rest, having no relative motion. If you now move at 2 meters per second towards the front of the train, the man in the train sees you moving at 2 meters per second relative to him in his own frame, which to him is at rest with respect to the train. But the observer by the side of the rail track will see you moving with respect to him at 12 meters per second. If instead you move 2 meters per second towards the back of the train, the observer in the train sees you moving at minus 2 meters per second relative to him, and the observer on the ground sees you moving at what velocity? At 8 meters per second relative to him. Are you okay with that? Can you hear me?
Yes, sir.
Yes, sir. Sir,
Yes,
please come
Yes,
again.
sir. We can
Yes,
hear
sir.
you. Yes, sir.
Of course, you will get these slides today.
Okay,
So
sir.
that I'll go
Okay,
back this
sir.
again.
Okay, sir.
It's quite simple. So let us look at a man that's on a train, and there's also another person on that train with him. As far as the man in the train is concerned, the observer on the train, the man is at rest, right? Unless he starts moving. If the man is moving 2 meters per second towards the beginning, the front of the man in the train, we see him moving at 2 meters per second, right? Relative to him.
Yes.
But the man by the rail track, we see him moving at 12 meters per second since the train is already moving at 10 meters per second. Agreed?
Yes, sir.
Yes,
So
sir.
suppose the man is moving towards the back of the train. The man in the other man in the train, we see him moving at minus 2 meters per second, right? While the man by the rail track, we see him moving forward at 8 meters per second.
Right, right.
Is that okay, right?
Yes, sir.
Move at
Okay.
change more.
Sorry, sir. Was it applied also in a lift?
So if you're in a car in uniform motion and you toss a coin vertically upward, you are imparting the initial velocity of the car to the coin, right? So the coin,
Yes.
as far as we are concerned, goes vertically upwards and drops right on the spot in your hand from which you tossed it. Hello? Yeah. Okay, my worry, Oshé. Sorry about that. Provided the car maintains its velocity, right? If it slows down, how does the coin drop? The coin will drop ahead of the point of launch, right? If the car speeds up, it drops behind the point of launch. What will an observer by the side of the road see? You will see a projectile motion with a horizontal velocity and vertical motion due to gravity, right? Do you agree?
Yes, sir.
Yes, sir.
So why is it that the body that you threw vertically upward has an initial velocity horizontally? Because you are moving at a horizontal velocity when you tossed it, right? That is why you should not jump down from a moving vehicle. So if a car is traveling at 120 kilometers per hour and an individual jumps from it, as far as it's concerned, is jumping down straight, right? Is it jumping down straight? No. It's going to be moving forward at 120 kilometers per hour. I know the damage the body will suffer if it hits the ground at that speed. Of course, gravity is also pulling the person down, so the person will experience projectile motion for a projectile launch horizontally. In just the same way, when an airplane drops an object, somebody from an airplane drops an object, there will be an initial velocity in the direction of the plane. Okay, let us look at linear motion. We are quite familiar with that. That's motion in a straight line. Let's look at speed, velocity, and acceleration. The speed of a body is the distance it travels per unit time. And distance and time are both scalars. Their ratio, which is speed, must also be a scalar. Scalar over scalar will give you scalar. Unit of speed is that of the ratio of meter to second, that is meter per second, per mile in
Shut up. Shut up. Shut up. Shut up.
is distance over time.
All right. Alpha, why is there no YouTube class for the thesis?
I don't know.
I just noticed I've not been sharing and I've not been recording to the cloud. Perhaps you don't need that part, right? Let's just move back so that part will be in the recording. Okay?
Zainab, don't let me repeat myself.
Who's that disturbing me?
Zainab, what's the phone? Whatever I tell you.
Hello, sir.
Yeah?
Sir, please tell people to mute themselves. I can't hear what you are saying.
You're all muted here.
Okay, sir.
You're all muted. If someone was not muted, such a person would have come up on the attendance list, on the list of participants. So speed is distance over time. As an example, a man cycles a distance of 80 meters in 10 seconds. Calculate his speed.
Okay.
That will just be equal to 80 meters over 10 seconds, which will be 8 meters per second. When you go from one place to another, most times you slow down, speed up, slow down again, speed up, on and on. It's almost impossible for you to maintain a steady speed in reality, in real life. In such a case, the average speed is defined as the total distance traveled per unit time.
You're supposed to enjoy something on board for you people to understand.
So if you rested during that period of time, or you stopped to eat, or stayed in a hotel overnight, all the time taken will be added together as total time. So that speed is always positive. Since neither distance nor time taken is negative. As an example, a man leaves Lagos at 8 a.m. heading for Ibadan, a distance of 120 kilometers. He arrived at the toll plaza, a distance of 50 kilometers, at 8:45 a.m. and stopped to buy fuel. At 8:50 a.m., he set out from the fuel station, finally arriving at Ibadan 9:10 a.m. Calculate 1. His average speed between Lagos and the toll plaza. 2. His average speed between Lagos and Ibadan. The distance traveled is 50 kilometers and the time taken is 45 minutes. That is for the first part of the journey. So his speed is 18.52 meters per second. Total distance traveled is 120 kilometers and the time taken is 70 minutes. So the average speed is going to be 28.57 meters per second. Is that okay so far? Straightforward. This is like what you met in your various secondary schools. Let us now look at velocity. Velocity of a body is the time rate of change of position. It's a vector measured in meters per second. As is the case with speed, we could define the average velocity as the change in position per unit time. The final position minus initial position over time taken. If you take a look at that graph, and this is not a straight line graph.
He's just talking.
You are now the one talking. Look at the graph. It's not a linear graph, is it?
No, sir.
That means that the line drawn from S1 T1 to S2 T2, that straight line is just an approximation to the curve. It is not the curve itself. So if we find the slope of that line, it's going to be just the average slope between time T1 and time T2. Taken?
Yes, sir.
What's the average velocity then? Final position minus initial position over time taken, which will be S2 minus S1 over T2 minus T1. As against instantaneous velocity, which is the time rate of change of displacement, which can be achieved by letting T2 tend to T1 in equation. That should be that equation. That equation you can see above. That's equation 1. That we should call it equation 1. So that's going to be ds dt. You've been taught differentiation in your various secondary schools. Most of you are taught differentiation. That's how you define the instantaneous rate of change between T1 and T2. If you allow T2 to tend to T1, what you then get is a tangent to the curve at time T1. This is the slope of the function at time T equals T1. You can see that the instantaneous velocity is not constant between T1 and T. Can it be constant? No.
No,
If
sir.
you look at that graph, you can see if you draw a tangent to that curve at different points in time, will they be parallel? No. They will not be parallel, which means that their slopes are not the same. It's only when you have a straight line that the slopes will be the same from one point to another. So under what condition will the instantaneous velocity be equal to the average velocity? Note that the slope to a straight line is the line itself or a line parallel to it. As such, the slope of a straight line is constant. So you can see that average velocity will be equal to instantaneous velocity if the graph of s versus t is a straight line. The slope of a straight line is constant. For such a situation, the velocity is constant and the body is said to be in uniform motion. You can therefore say that instantaneous velocity is equal to average velocity only when the body is in uniform motion, as you can see in the figure on that page. Notice that in this case, the straight line is not an approximation to the curve. It is the motion, it actually shows the motion of the body. Unlike the previous situation in which the straight line is just an approximation to the curve. Can you see that?
Yes, sir.
Yes.
That's very important. The slope of an ST graph is velocity, and the area under the ST graph is the distance traveled by the body. When you say a body is in uniform motion, if it makes equal displacements in equal intervals of time, this will mean that its velocity is a constant. The velocity is constant only if its magnitude and direction are both constant. You know, a vector has both magnitude and direction. For a vector to be constant, it must be constant both in magnitude and in direction. So take a look at uniform circular motion, for instance. A body is going around a circle at a uniform speed, but the direction is changing at every moment. Such a body cannot be in uniform motion. It can only be in uniform circular motion. The body is in uniform motion if it makes equal displacement in equal intervals of time. This means that its velocity is a constant. The vector is constant only if its magnitude and direction are both constant. Since the magnitude of the velocity is the associated speed, constant velocity will mean the speed must be constant as well as the direction. Therefore, a body in uniform motion must be on a straight line and must have a constant speed. A body not moving on a straight line is not in uniform motion, even if its speed is constant. Such a body is in non-uniform motion. And of course, the body is in non-uniform motion if it makes unequal changes in displacement in equal intervals of time. We have seen velocity. Let us now take a look at acceleration, which is the time rate of change of velocity of a body. It's a vector measured in meters per second squared. Just as you had it under velocity, the average acceleration is defined as final velocity minus initial velocity over time taken. I just repeated that graph. Changing, oh, that should be V2 minus V1, please, not S2 minus S1. Copy and paste. In that graph, be V2 and V1 minus V1, as you can see in the equation that follows the graph. And that should be final velocity. Oh my goodness. That should have been average acceleration equals final velocity minus initial velocity over time taken. Copy and paste. Instantaneous acceleration, just as we had instantaneous velocity, is the time rate of change of the velocity, which we get by allowing T2 to tend to T1 in that last equation, this last equation here. So that is going to give us dv dt, which is limited at T2 tends to T1, V2 minus V1 over T2 minus T1. This is the slope of the function at the time t equals T1. You can see that the instantaneous acceleration is not constant between T1 and T2. You've seen it in the case of velocity. Just think along the same line. The average acceleration will be equal to the instantaneous acceleration if the velocity versus t graph is a straight line. The slope of a straight line is constant. For such a situation, the acceleration is constant and the body is said to be uniformly accelerated.
Nice.
We can therefore say that instantaneous acceleration is the same as average acceleration if and only if a body is in uniformly accelerated motion. Any problems so far?
Yes, sir.
Okay. Are you enjoying the class?
Oh,
No.
No,
so that
no,
All
sir.
right. Okay, just dust it up later. Notice that in the straight line journey, the function I just repeated, you see, it's as if I'm repeating the whole thing again. So you should be able to enjoy the class. It's an approximation to the graph. While in the straight line, the line is not an approximation, but the graph itself. It's often good to think of acceleration of 5 meters per second squared as a velocity increasing steadily at 5 meters per second every second. That is 5 meters per second, which is 5 meters per second squared. A body is uniformly accelerated motion if it makes equal changes in velocity in equal intervals of time. And it's in non-uniformly accelerated motion if it makes unequal changes in velocity in equal intervals of time. And you can turn around again. You can say a body is in non-uniformly accelerated motion if it makes equal changes in velocity in unequal intervals of time, right? If it makes equal changes in velocity in unequal intervals of time, so that will still be non-uniformly accelerated motion. But in that case, the numerators will be the same, but the denominators won't be the same. So the ratio is not going to be the same. We can illustrate all this in a single graph. Look at the ST graph. The horizontal line has slope 0, right? And since the slope of an ST graph is velocity, the velocity is 0. Take a look at the next set of lines. One is slanting, increasing to the right. The other one is reducing to the right. Since the lines are straight, they denote uniform motion. But for the first one, velocity will be greater than 0. For the second one, velocity is less than 0. In each case, velocity is constant. Then the third standalone graph there, the last graph, is for non-uniform motion. You can see the slope to that curve cannot be constant. So velocity is not constant for that one. So it is not uniform, does not depict uniform motion. Take a look at the next graph. This one is now a VT diagram. The first one, horizontal line, parallel to the time axis, is A equals 0. A is 0 because velocity is not changing. Then the next set, uniformly accelerated motion, A constant greater than 0, A constant less than 0. And the last one, non-uniformly accelerated motion, in which acceleration is not constant. Deceleration or retardation. Acceleration that is opposite velocity is called retardation. It applies only if the body is slowing down. The body is going to the right and slowing down. The acceleration is to the left and negative. Do you understand? If it is slowing down, then the acceleration is to the left. Since our friend is moving to the right, acceleration must be opposite the velocity. That is why it is slowing down. The retardation is the negative of the acceleration. Thus, if a car is moving to the right and slowing down by 2 meters per second every second, the acceleration is minus 2 meters per second squared. And the retardation or deceleration will be 2 meters per second squared. In this case, the acceleration is opposite in direction to the direction of motion. Therefore, it is slowing down. If the car is moving to the right, it suffers retardation only if it is slowing down, meaning that there is an acceleration to the right. That should be left. Opposite is motion, as I said earlier. The acceleration is the retardation. Note that not all negative acceleration is deceleration. If the car is moving to the left and speeding up, then its acceleration is negative. It is not decelerating because it is going faster. You know that. It is not decelerating, even though the acceleration is negative because it is going faster. So deceleration applies to slowing down. If it is slowing down while going to the left, the deceleration will be positive, the same as the acceleration. As another example, when the body is projected vertically upwards, it suffers retardation on its way up because the acceleration due to gravity is directed downwards. It slows down until the velocity is 0, then it starts coming down. The velocity keeps increasing as both velocity and the acceleration are now in the negative direction, or put another way, in the same direction down. As this acceleration is negative, but the body is not in retardation. You have seen this before, equations of motion, uniformly accelerated motion. What we are taught in secondary school, V equals U plus 8, S equals U plus half 8 squared, V squared equals U squared plus 2AS, and S equals U plus V over 2 times T are all equations of uniformly accelerated motion. They don't apply if acceleration is not constant. As you can see in that figure, acceleration is constant because that's a linear graph. with the velocity of the body increasing from u at time t equals 0 to v at time t equals t. Now consider the general case of a body that is uniformly accelerated from an initial velocity u to a final velocity v, as I said. It means that the body did not start at rest. The body starting from rest is a special case of uniformly accelerated motion. The slope of the line is the velocity of the body. So A is v minus, so that should be acceleration of the body, please. The slope of the line is acceleration of the body. So A equals v minus u over t. Hence, v minus u equals at, cross multiplication. If we rearrange that, v will be equal to u plus at. Now let us look at the area under that curve. You know there are two bits to it, the rectangle and the triangle. The rectangle has a length t and a height u. What is that area? That area will just be ut. Then the triangle has height v minus u and base t. So the area of that triangle is half base times height, which is half of t times v minus u. If you put all that together, you arrive at ut plus half t into v minus u over t times t. What did I do? I just divided by t and multiplied by t. Can you see that? I divided minus u by t and multiplied by t. Have I done anything wrong? No. Let's see what happens next. So do you recognize v minus u over t? That is a. Then t multiplying t, the two t's on top will give you t squared. So you get ut plus half at squared. You can find the area under the VT graph using the area of a trapezium with parallel sides u and v and perpendicular distance between them t. Let's take a look at that figure again. That's a trapezium, right? This is a trapezium. That parallel side. What are the parallel sides? U and V, right? U on the left, V on the right. And the perpendicular distance between them is t. So half sum of parallel sides multiplied by the perpendicular distance between them. The parallel sides are U and V. So half of the sum will be half into U plus V, right? Then multiplied by t. That's it. Which will be half into U plus V. Instead of writing t, I wrote V minus U over A. T is V minus U over A, isn't it? Take a look at A equals V minus U over T. Just swap A and T. T will become V minus U over A, right?
Yes, sir.
Yes, sir.
You get 1 over 2 into V plus U into V minus U. V plus U into V minus U is difference of two squares. That will just be V squared minus U. So S will be equal to 1 over 2A into V squared minus V squared. To rearrange that,
So when you like my own now, I use my own personal money. I use my
Which is the money you used before.
Mute your mic. Mute your mic.
5,000.
Mute your mic.
So hard. Just speak, Mike.
those village girls. Okay. We retain the formula we saw earlier, which is S equals U plus V over 2 times T. We now interpret this to mean that the distance traveled, that's not average velocity. That's average of the velocities, not average velocity. Average velocity is final velocity minus final position minus initial position over time taken. So that's not average. This is not average velocity. It's the of the two velocities at the beginning and the end of the journey, multiplied by the time taken. Note that these equations are all for uniformly accelerated motion only. That is why questions that require you to apply equations have accelerate uniformly. unless the acceleration is specified. How should you use these equations? As much as possible, make use of what you are given, and only what you calculated only if you are constrained to. This is because if you make use of a value you calculated and made a mistake in the calculation, this mistake will be carried forward into other calculations. Let's take an example. A boy starts from rest and accelerates uniformly at 2 meters per second squared for 5 seconds. Draw the VT diagram, calculate the final velocity, calculate the travel. U is 0 meter per second because it started from rest. A is 2 meters per second squared and T is 5 seconds. So you can sketch that. And then, well, if you take a look at that diagram is not complete. That should be 10 meters per second. You should first take question 2 before taking question 1. So V, as you can see in that figure, should have been 10 meters per second. So V equals U plus 80, which is 0 meter per second plus 2 meter per second squared times 5 seconds. That will give you 10 meters per second. Here you can make use of one of the formula equals U plus V over 2 times T. Equals 2T plus half AT squared, or V squared equals U squared plus 2S. Which one are we going to use? We are given the initial velocity and the acceleration. Which one is best for us to use? S equals T plus half
plus
AT.
V over 2T.
All the two other equations involve V, which we calculated. So if you make use of the second equation, S equals that, and I'm going to arrive at 5 meters. I believe which one of us can handle that. The body moving at meters per second accelerates uniformly to 10 meters per second in 4 seconds. Draw the VT diagram, calculate the acceleration, calculate the distance traveled. This one is pretty straightforward because we are given both the initial and final velocities. So the VT diagram is switched to draw. A is minus U over T, which is 2.5 meters per second squared. And S is, since we are given both U and V, make use of this formula, V plus U over 2 times T, you get 28 meters. I believe you can all take question 3. The only thing that is challenging there is calculate the distance traveled in the 5th second. Then calculate the distance traveled between the 3rd and the 5th seconds. Calculate the distance between the 3rd and the 5th seconds. Let's look at lap 1. U is 0 meter per second, A is 4 meters per second squared, and T is 5 seconds. Why do we deal with laps? Because the acceleration is not constant throughout. We have to break the journey into bits over which the acceleration is constant, because our equations apply only to cases of uniformly accelerated motion. So we first calculate the final velocity for the first lap, so we can draw the VT diagram. So V equals 20 meters per second. We can now draw the VT diagram as shown. So for lap 1, we're trying to calculate S. We use S equals UT plus half AT squared. Should we use UT plus half AT squared? Yes, you are given U, A, and T. So that's the formula you use. S equals U plus V will not work in this case, or should not be used because you calculated V. For lap 2, look at lap 2. That is uniform motion. Actually, U should be, what's U? U is 20 meters per second, not 0. That should be 20 meters per second. A is 4 meters per second squared, and T is 5 seconds. In this case, the velocity is uniform, just 20 times 10, right? 20 meters per second multiplied by 10. Why 10 seconds? 15 minus 20 minus 5, that's 10 seconds. The second lap lasted only 10 seconds. So please, this is 20 meters per second, not 0 meters per second. Meter per second. 3. The total distance traveled is the trapezium. This is a single trapezium. If, for instance, the body goes to rest uniformly, you still have a single trapezium. But when the body does not start from rest and then goes to rest, it's no longer a single trapezium. You have two trapeziums, or trapezia as you may wish to call it. So we use area of trapezium. I believe we can all do that. What are the parallel sides now? 10 and 15, right? Side of the trapezium is 10. The lower side is 15. So half plus 15 multiplied by the perpendicular distance between them, which is 20. That is 250. If the acceleration is constant, the distance traveled between time t1 and time t2, the distance traveled at the end of time t2, t equals to minus distance traveled at the end of time t equals to, which I just told you is 50 minus 10, as we saw in the other case. Let us now look at the distance traveled between t2 and t1. What do? We look at s at t2 and subtract from it s at t1. That will be ut2 minus half a t2 squared minus ut1 plus half a t1 squared. If you rearrange that,
Yes, sir.
thank you. If you rearrange that, you get u into u is common, right? Because the velocity, initial velocity is the same. U into t2 minus t1 plus half a into t2 squared minus t1 squared. The distance traveled in the 5th second is distance traveled at the end of the 5th second minus distance traveled at the end of the 4th second. U is 0 meter per second, A is 4 meter per second squared, T is 4 seconds, and T2 is actually that should be T1. T1 is 4 seconds, and T2 is 5 seconds. So S at T2 minus S at T1 will give you U into T2 minus T1 plus half into A T2 squared minus T1 squared. Since U is 0, the first part on the right hand side will be 0. You are left with half into 4 times 5 squared minus 4 squared. Maybe 2 times 9, which is 18 meters. Between the 3rd and the 5th second, this is what you are going to have. Just like the last one, the distance traveled will be 32 meters. Alternatively, you can calculate the velocities at times t1 equals 3 seconds and t2 equals 5 seconds. In this case, we already know that v at 5 seconds is 20 meters per second. V at 3 seconds will be 12 meters per second. Perpendicular distance between these parallel sides is 5 minus 3, which is 2 cm. We apply the area of a trapezium. You get s equals half into 12 plus 20 times 2, which is 32 meters again. Now use this method to solve number 4. For number 5, between the 3rd and the 8th second, other figure, the acceleration is not constant in this case. It is the same between the 3rd and the 5th seconds, but not between the. By the time you get to the 5th second, it's no longer the old acceleration, is it? It's now uniform motion. So you're going to calculate in 2 different bits. The rectangular part gives an area 3 times 20 is 6 meters. The distance traveled between the third and the 8th seconds is 32 meters plus 60 meters, which is 92 meters. Because we already calculated the distance traveled between the third and the 5th second. We just added the extra 60 meters to make it 92 meters. Very much the same. I think you can handle that on your own. All these ones, the child's play. Any questions so far?
Yes, sir. Sir, please can you go back to that lab 2 in Roman figure 2 of the number 3? The number 3 question we solved. I don't understand how you did the lab 2.
Yeah?
Yes, lab 2 here. Roman figure 2.
Also, as I said, 20 meters per second, not 0.
Okay, here is
Okay.
20 meters.
U is 20 meters per second. U is 20 meters per second, not 0 meters per second. Is it okay now?
What of the acceleration?
Lab 2.
Yes, for lab 2. Is there any acceleration for the lab 2?
You have a point there. There's no acceleration, so it should be 0. Is that okay?
Okay. So, sir, please, which formula do you use? Sorry, that's the last one. For the lab 2. The lab 2, like we are giving you and we're
U
giving.
is 20 meters per second. A is 0.
Okay.
Yeah. T is 5 seconds.
Thank you, sir.
That's the old one you were taught even from primary school. S equals UT.
I don't understand.
Distance traveled is velocity times time. That is because acceleration is 0, right?
Yes.
Just 20 meters per second times 5 seconds. Oh, the time is 10 seconds. You see, it's just copy and paste. I just copied lap 1. Look at lap 1. U is 0 meters per second. A is 4 meters per second square. T is equals 5 seconds. I just copied it without editing it. Is that okay now?
Thank you.
So lap 2 should be U equals 20 meters per second. A equals 0 meter per second square. And T equals 10 seconds. Is that okay?
Yes, sir.
Okay. A bullet fired into a wooden block loses 1/4 of its velocity after penetrating 50 cm. How much further does it travel before coming to rest? Since the acceleration is assumed to be constant, acceleration during the first part of the journey is equal to acceleration for the rest of the journey. The first part is a reduction from v to v over 4, and second part, a reduction from 3v over 4 to 0. If the velocity reduces to v over 4, what is the velocity? Loses 1/4 of its velocity. That should not be a reduction from v to 3 over 4, but a reduction from v to 3v over 4, right? Is that okay? Hello?
Yes, sir.
That should have been a reduction from v to 3v over 4, not a reduction from v to v over 4. I'll try to edit all this again before getting it across to you. Is that okay?
Yes, sir.
Yes, sir.
And the second part, reduction from 3v over 4 to 0. So v squared minus u squared equals to a. A is constant. That will be 3 over 4v all squared minus v squared over 50. That will be 0. Well, that should be 0 squared. Which should be 0, right? For the last one, which should have been 0 squared minus 3 over 4v all squared. Is that okay?
Yes, sir.
So that middle one again is faulty. But the one after that is correct. 0 minus 3 over 4v all squared. Well, this is going to need a lot of editing. But in the end, you are going to get S equals 9 times 50. Okay, that's 7 over 50 equals 9 over S. You are going to get S equals 64.29 C. I will edit it and send it to you. Some elements of differentiation. Let's look at polynomials. ddx of x to the power n is nxn to the power n minus 1. For example, what is ddx of 3x squared minus 2x to the power minus 3 plus 3x plus 2? That will be the power you come forward, right? You get 2 times 3x. Now x will be raised to power only 1. Then minus 3 will come forward and multiply to minus 2 to give you plus. Then the power of x is equal to x power minus 4. And then 1 will come forward and multiply 3. You get 3. X will now be 1 to x to the power 1 minus 1. X to the power 0 is 1.
Why?
You get 6x plus 6 x to the power minus 4 plus 3. Which will be 3 into 6 plus 2 by x to the power 4 plus 1.
You are moving too fast.
Velocity v is dx dt. If x of t is 3 to minus 40 plus 2, v will then be dx dt, which will be 60 minus 4. When will the velocity be 0? It will be 0 when 60 minus 4 equals 0. Or put another way, t equals 2 over 3 if t is in second. The displacement is maximum when the velocity is 0. And the body stops and reverses. The maximum value of x in this case is got by putting t equals 2 over 3 expression for x. See, we have got the minimum, the value of t at which the velocity is minimum, right? Or maximum. Okay, this is maximum when the velocity is 0, right? Is that okay? Okay, let's take a look at a body that is going up. What is v? Minus t, right? Hello? V is u minus g. When is velocity 0? At the maximum point height, right? Then u minus g will be equal to 0. What will t be? U over g. How do you get the maximum height attained? You substitute that t into y equals ut minus half gt.
Sir.
What you get to be the maximum height attained?
Not seeing the slide of that you explained.
Squared over 2g. So the displacement is maximum, just the way the maximum height is attained when the velocity is 0 and the body stops and reverses. Maximum value of x in this case is got by putting t, just the way we did for motion under gravity, into the expression for x. X at t equals 2 over 3. Just put 2 over 3 into this expression for t. And then you're going to get 2 over 3 meters if x is in meters. The acceleration is described which is speed of 60 minus 4, which is 60. What kind of motion is this? Uniformly accelerated motion.
We don't understand. We are moving too fast.
We don't understand anything.
Sir, we don't understand anything that we are saying. We don't understand anything.
Relax now.
Sir, we understand. Move on. Understand.
We don't understand anything.
Sir, we understand. Move on.
Okay. Hello, we have just a few minutes left. Let them ask the question.
Sir, we don't understand anything, please, sir.
I want to see the slide explaining.
Nothing. We don't understand.
Let's go back to this.
I don't understand.
You don't understand. Maybe you did not do calculus in secondary school.
Sir, us, we understand.
Exactly. We do
Leave them alone. Sir, we understand.
We understand. Move on. We understand. It's application of differentiation.
Okay. I know some of you went to take civic in secondary school. So civic is compulsory. Some of you did not take further maths.
Yes.
So
Yes.
Yes, sir.
Differentiation.
Yes, sir.
Differentiate. That's why I give you. This is when you get home. Take a look at this again. We start from here next class. So I see you on Thursday. Our time is up. All right. You have a wonderful day.
Okay, sir.
Okay, bye bye.
Thank you, sir.
Sir,
We love you, sir. We understand the
Have a
class.
wonderful day.
We love you, sir.